Welcome to today's IEEE Geoscience and Remote Sensing Society webinar. We're so glad you're joining us. United by the mission to advance geoscience and remote sensing, GRSS is dedicated to knowledge sharing by ensuring transparent, accessible, and collaborative learning for all. And our webinars are just one way we bring that commitment to life. Designed for students, early career researchers, professionals, and enthusiasts, these webinars address foundational topics as well as a wide range of emerging subjects, while also offering sessions on academic writing, publishing, and career planning. Our webinars are made possible through the collaborative efforts of GRSS's technical committees and various other initiatives, bringing together a diverse community of experts to deliver high-quality learning content. During the webinar, please submit your questions through the Q&A feature, and they'll be addressed at the end. You'll be asked to complete a survey afterwards, which helps us tailor content to your interests. Be sure to check out the IEEE GRSS YouTube channel for previous webinar recordings in case you missed any. And for updates on future webinars, visit the GRSS calendar and follow us on social media. We're excited to have you with us. Let's dive in.
All right, after this short video from GSS, welcome everybody. I'm Ronnie Hensch. In my day job, I'm with the German Aerospace Center close to Munich in Germany. But I'm here because I'm the past chair from one of the technical committees of GSS, the Image Analysis and Data Fusion Technical Committee, IDF for short. And while I'm the past chair, I still have a couple of roles or responsibilities inside of the TC, and one of them is organizing webinars. And when I took over, I designed 3 different tracks for 3 different types of webinars. One is called Earthwise, where we address applications of applying computer vision to Earth observation imagery. The other one is Crosstalks, where I invite people outside of our community, so outside of remote sensing and Earth observation, more like core computer vision, core machine learning people, to give talks about their topics that are still very relevant to us, of course. And then the third one, and we have one talk in this series today, is Orbit Tracks, where I invite people who are working at the intersection of computer vision and Earth observation to advance methods, basically, right? Today we have, I think, the second or third talk in this series, and I'm very happy to welcome Valerio, who is our speaker today. So I will keep my talk short so that we can really focus on his topic. Valerio did his PhD at the Sapienza University in Rome a couple of years back. And after that, he held a couple of postdoc positions in France at CNAM and in Belgium at the KU Leuven. And now he's a research fellow with the ESA Phi-lab. Probably most of you know the Phi-lab, right? They are really focusing on really strong machine learning, computer vision for all types of Earth observation data. And his task there is very much focused on Geospatial Foundation Models. And this is also what the talk today will be about. And I'm very happy that you're here, and I hope you will enjoy the talk. I'm very sure I will. So without further ado, Valerio, the floor is yours. Please go ahead.
Thank you, everyone. Good morning. I'm going to share my screen so I can help myself with some slides. So
just before you start, it was in the video, but I just want to repeat that. Feel free to ask questions, just put them into the Q&A box, and then we will address at least some of them, depending on how much time we have at the end after the presentation. But you can ask your questions at any time, and then after the presentation, we will go through all of them. All right, thank you. Enjoy.
Okay, so you can see my presentation, right?
Yes, all there.
Okay, perfect. Okay. So I'm Valerio Marsocci. Thanks for the introduction. I'm not gonna lose some more time about myself. So let's just dive into what we're talking about today. So we're gonna talk about PANGAEA that maybe some of you already know, and other funny things very related to Geospatial Foundation Model. Once again, if you have any kind of any question, please drop in the chat, and we're gonna in the future Q&A feature, and then we're gonna answer later. But I wanna start asking you a question that is, okay, let's think about a real-world use case. And for example, okay, in this case, I selected, for example, some Sentinel-1, Sentinel-2 images to solve some biomass estimation task. In this case, of course, we're thinking about a regression task. Okay, so to solve this kind of task, we can use a model, any kind of model that could be a unit or any other kind of the best model, the model you prefer that can just solve some dense tasks. But what if we think about another task that could be change detection? And in this case, we have just two very high resolution images in which we want to map changes. So it is a classification task because we don't want to have a continuous values in the output, but just a discrete values of 0 and 1. And we have very different resolution. We have different kind of images. So we don't have radar images, but just optical images. And we have just bitemporal images, while in the other case, we could have either multitemporal or single temporal. And my question is, okay, in this case, also, you can just think about a model. So again, it could be a unit, could be another model. But what if we want to use the very same model to solve both tasks? How would you do it? Of course, the answer is kind of straightforward because today we're talking about Geospatial Foundation Model, but yeah, we want to use a Geospatial Foundation Model. So basically, what is a Geospatial Foundation Model? Is a very big model that in our case mainly could be computer vision model, but not only, we're gonna see. But that is pre-trained on a massive amount of data. And which are the characteristics of this Geospatial Foundation Model? So when can we call a model a Geospatial Foundation Model? Mainly, we identified 5 characteristics that are task agnosticism, that it means, as I showed you before, that with the very same model, we want to solve different tasks. So we are pre-training the model, not to solve just one task, but more than one. And in the one I showed you before, okay, we have regression task, classification task, change detection, and so on. Then we want it to be spatio-temporal aware. That it means that it works in any time, in any place. So it means that the features that we are learning are independent from the area on which it was trained and the time step in which it was trained. And again, we saw in this task that, for example, we can have multi-temporal or bitemporal or even single temporal models. Then we want it to be sensor agnostic. And this means that, okay, we talk about task agnostic, but sensor agnostic, we are referring to the kind of images that we're inputting the model. So again, we can have optical images, we can have radar images, we can have LiDAR, hyperspectral, and so on. But even if we are considering, for example, one modality, so for example, optical images, we can have different sensors that have different characteristics. So for example, in this picture taken from DOFA paper, we can see that even if we're considering optical images, we can have NIPE, so very high resolution. We can have Sentinel-2 that have more bands. We can have GFMs. So we can have different sensor characteristics. But then this is very connected to the multimodality. So of course, when we're referring to multimodality, we refer to the fact that we can have, okay, different kind of images. So again, radar, optical, whatever, but also other kind of data that are not just computer vision based, but a lot of data that generally are lately not that much, but I mean, they were kind of underlooked so far, like text, but also just the metadata. Most of the metadata are just discarded. And this is true for some kind of data like SAR, they're still kind of underlooked. And then all these models should be adaptable in the sense that we want to use them for different tasks, but we want to, let's say, slightly fine-tune or even not fine-tune at all, but they should be versatile to solve all these tasks. Now that we understood what is a Geospatial Foundation Model, more or less, okay, we want to say, okay, now we have these 2 tasks. We want to solve these tasks with the same model. Which model should I use for my tasks? Well, there are so many at the moment, and we have to find a way to, and this is just an example, they are not even all of them. We have to find a way on how to select the best one. Well, the best way to do it is to benchmark these models and find out. Why benchmarking is important? Well, it is important because of 2 main reasons that are leading then to a third one. The first one is that, of course, we want to understand, given that most of these models, most of these papers are come with their own benchmarks for sure, for some reason that are totally legit. So most of them want to focus on some downstream tasks, some other on some just technologies, some methodology more than the results. But most of these in the research papers are coming with their own benchmarks. So there is not an established benchmark. So it's kind of difficult to evaluate the performances across these models. And so this is the very first important stuff for why benchmarking is important, because we want to understand how, under which condition, a model is better than one other, and vice versa. And also, this is, of course, very important because we want to assess the fairness and robustness of these models. In fact, we know that some areas are kind of underrepresented, some tasks are underrepresented, and we want to understand also if having a representative, diverse benchmark, these models that are, for example, shaped in some area and tested in some area of our world could work also in other areas. And of course, after we can assess the performances in these two ways, we can also get the improvements of the new models. So understanding why they're failing, when they're failing, we can understand how to make better models. To do so to benchmark models, we developed PANGAEA. PANGAEA is a strong evaluation protocol. It's no more than this, in which we put together different models and we put together different datasets. Of course, as I told you, concerning the datasets, we wanted to have a diverse benchmark. And for the model, we are gonna talk about this later. But basically, what we really want to establish is a protocol that could be reproducible and could be robust enough so that the results are reliable. And there are, in this way, again, we can understand which are the limitation and the strengths of our Geospatial Foundation model. If we get back to the datasets, I can tell you that, as I told you, we tried to include several diverse datasets that were already established in the community. So we selected based on, for example, different domains. And as you can see, we have domains that can vary from disaster mapping, so for example, wildfires, flood detection, and so on, to agriculture, and also for agriculture, within the same domain, we have different tasks. So we can have, for example, boundary delineation, we can have crop mapping, and so on. Also, in the type of task, we have different tasks because we have classification, we have change detection, we also have regression that is not in this slide, but okay. For example, about forest, so biomaster is the dataset included. And also we have different resolution of the data in input. So we have, for example, kind of low resolution, like harmonized Landsat Sentinel data, so 30 meter per pixel resolution, but we have also GFM2 that is kind of high resolution. And on the other side, we have also, of course, SAR data with different preprocessing level and so on. We also tried to make it, again, inclusive from a geographical point of view. And so we try to cover at our best most of the world. And not all the countries are covered, but we're trying to improve this. If we want to focus on the models, well, this was developed like 1 year ago. So we took all the models at the time that were open source, well established in the community, in the sense that they could have either the code was adopted or the paper was published in a high-level conference and so on. And the technique should be, let's say, innovative in the sense that we try to cover different novelties, different methodologies. As you can see, for example, we have some baseline like SSL for your S12. We have a very high resolution Geospatial Foundation model like ScaleMA. We have models that were supervised, so in which the pre-training step was a supervised pre-training step, like SatLasNet. Some other that were using text, like Remote Clip, or some other were combining different other techniques, like for DOFA, they used a very cool wavelength encoder. In Chroma, they were using Alibi and contrastive learning, and so on. And so with this dataset and with these models, we put this evaluation protocol together, in which, for example, we use the UberNet as a decoder. We froze our encoder to see how these features were used, and we performed a very large set of experiments, and we are reporting just some of them today. So basically, if we want to focus on the main one, okay, this is just a wall of text. I'm going to help you. We're going to see that benchmarking all this model against the baselines, we can see that some baselines are still doing the best, let's say. So UNet is working very well if you know nothing about your task, in the sense that if you know nothing about your downstream dataset, so the input data, the task itself, or about your Geospatial Foundation model, well, I would suggest you to use the UNet because it's kind of, in average, is the best. So it's having top 2 results 6 times out of 11. But of course, there are some, Geospatial Foundation model are still some cool stuff to investigate, because there are some cool patterns that we identified. So for example, if we focus on the resolution, so let's say on the sensor better, we can see that there is a strong correlation between the pre-training.
Valerio, sorry
Yeah.
to interrupt you. There's the Zoom box that you're sharing your screen at the bottom of your screen. Can you click
Yeah,
on,
okay, yeah.
can you click on hide because it's blocking
Yeah,
some
yeah,
of the
sorry.
text? Thanks.
Sorry. Okay, so yeah, we observed that there is a very strong correlation between the pre-training sensor, so basically the sensor that were used for pre-training, and the downstream sensor, so the data that were used for the downstream task. And if we want to focus, for example, on high-resolution data, we can see that, for example, GFMs WIN and ScaleMAE were two of the models that were pre-trained on very high-resolution data, and they're having the best results on GFM2, that is very high-resolution dataset. And in this case, for example, if you look also at the unit results, you can see that, so here, you can see that there kind of a huge gap. So it totally makes sense in this case to use a foundation model. And also if we see the other side, so for example, if we see like low resolution data, if we look at them, we can see that in the case of Sentinel data, Sentinel-1 and Sentinel-2, Chroma was pre-trained on this. And once again, it is kind of way better than using just a unit. So this is already a first take-home message. But then we observe similar correlation, but from other point of view. For example, if we look at into multispectral data, we can see, okay, once again, unit is doing good, but models that were pre-trained massively on just multispectral data can do even better, like, for example, in this case, Chroma once again. And on the other side, models that were pre-trained on very high-resolution data like ScaleMAE can do in average better than unit. While if we're focusing on data scarcity, we can really see also how unit step-by-step is getting, let's say, less robust and is more prone to have outliers. So both for 50%, in which we have kind of, again, less robust results, but also in 10%, we have really an outlier. So these are some results about PANGAEA, but more in general, I also want to tell you about what we did. So basically, we did this repository in which you can easily add your own dataset, add your own models, and okay, then we have this community that is still working on improving it, and we are going to talk about the improvement very soon. And just to prove that it's kind of easy to add your own dataset or your own model, I can tell you that it happened that, for example, people that we were not directly in contact with, so for example, the author of AnySat, used it autonomously, but also Tessera people used it. So several other papers adopted it, plugging their own model. And this is also very fruitful for the community, because then next people arriving will already have not just the models that we included in it, but also these new models. And on the other hand, we also used it for our purposes. So again, in ESA, along with IBM, along with DLR and with Jülich, we developed TerraMind, that is this large-scale generative model that is both generative and discriminative model for Earth observation, and is, let's say, the first of the new generation of Geospatial Foundation Model, in the sense that is one of the models that came in 2025 that are they're having good results, and along with it, once again, Galileo, Alpha Earth, AnySat, and so on. Sorry, Tessera, Olmert, all these models. Sorry if I forget some of this. And so this was the one that we really benchmarked on our dataset, and we observed that, yeah, basically it's having way better results than the average. So if you check the average, TerraMind is having kind of better results in average. And for this reason, now we're very open to the next steps, in which we want really to add new models, new tasks, new features. And okay, if we're talking about new models, I already mentioned some of them. I forgot about Copernicus FM, but yeah. About new tasks, now we're really working actively about adversarial attacks. So we want to see also, okay, this foundation model should be more robust, as I showed you before, is one of the tasks that we're more interested into. But what if we attack, for example, with white box attacks, these models, and we are observing that we have very, very bad results, so they're not really robust, but we're gonna follow up on this later in the next months. And we want also to add new feature, because we were asked this kind of feature from some people, for example, are more just interested in visual results or in embeddings and so on. But this slide is also to tell you that if you are interested in collaborating, or if you want to add some feature, we're really open to guide you through PANGAEA or even to work with you on this. But now, basically, I want to move on some other interesting task according, in my humble opinion, about the Geospatial Foundation Model. That is what I mentioned to you before. So basically, adaptability. And if we talk about adaptability, I'm gonna tell you about DEFLECT. That is a work that I carry on recently with a colleague from CNES in France. And basically, we consider once again some cool Geospatial Foundation model. And in this case, okay, some of them we already saw today. So Scale MA, for example, but some other are kind of new, let's say. So Cross Scale MA and DynMC. And again, once we selected this model because they have kind of different characteristics. So Scale MA is just master encoder with some Laplacian modules. Then Cross Scale MA is putting together master encoders and contrastive learning, while DynMC is based on Dyno, so it's working basically on contrastive learning and knowledge distillation. And these models are working very well on a lot of tasks, like the one we observed before. So once again, change detection with RGB images. So nothing to add. Okay, if we have an RGB dataset, these are very cool. But what if we need some more specific information? Like, for example, think of mapping marine debris. Okay, maybe this is with RGB, you can already map kind of well, but this is kind of more difficult. So what if the models that I showed you before are just pre-trained with RGB images so they can just work on RGB images? And basically, we're wasting all the multispectral info, for example, in this case of marine debris or any other task that you can think of, like agriculture and so on. Well, the straightforward idea is to fine-tune them. So we can just have this data, fine-tune end-to-end in some way to also have this multispectral info into our model. So to put this knowledge of multispectral info in our model. But out of this, we observed that there were some limitations, let's say. Which are these limitations? Well, some of them are already mentioned, but basically many models, now less and less, I have to say, but many models, mainly some of them are Geospatial Foundation Model, like the one I showed you before, are trained on single modality RGB. So basically, yeah, in the case of Scale MA, it was pre-trained on functional map of the world. So kind of very high resolution data. If I'm not wrong, they're maxer data, but like single satellite. But as we observed in the example that I just showed you before, multispectral data are very, very crucial for many tasks, like, yeah, again, marine debris, agricultural tasks, toxic industrial plumes, and so on. And one solution is the one I mentioned, so basically end-to-end fine-tuning, but as you know, it's kind of costly and heavy, and this is an issue not just because of time, but also because, for example, small realities, small labs cannot even afford it or don't have GPUs to do it. So it's a task that we should care about. So our idea was to use these strong priors that are already there, because, I mean, we are talking about very cool Geospatial Foundation model, so they know how to solve tasks on RGB, for example. So using these priors, so not wasting them at all, but adapting them better to solve also multispectral tasks. How to do it? We came up with DEFLECT, our solution that is made on two basically architectural innovation. There is an entangled patch embedding layer and an entangled attention mechanism. And based on an idea of deflecting the embedding. This is the reason why deflect, of course. That it means that we want, okay, we already have some clusters, some latent clusters, and we want just to adjust the trajectory of these clusters without changing the norm, because we want to preserve the norm, because this is one of the strong priors that we learned in the RGB step. If we want to jump into the model itself, well, as you can see, here we have our Geospatial Foundation model. And we have the patch embedder. There was a normal pre-trained patch embedder that we replaced with our UPE. And as you can see, there are no, we're gonna see more details later, but there are no parameters that are fine-tuned in it. So it's coming, I mean, we have new feature, new knowledge, let's say, with no parameters in addition. And then we are replacing not all of the attention block, but some of the attention block with our UAT, with our untangled attention block. And the idea behind is the one I told you before. So we want just to deflect the embedding without changing the trajectory of the embedding without changing the norm. But if we want to have more details on all of these mechanisms. Basically, yeah, for the untangled patch embedder, just to make it very, very easy, we have X, and we can divide X in XP, that is the RGB channels, and the XA, that are the new info that we have. For XP, we're just using the pre-trained patch embedder. So we're not changing anything, and this is all frozen. So we're just having RGB, and we are extracting the feature out of RGB with our pre-trained patch embedder. While for XA, so yeah, for our multispectral info, we extract just few information with no learnable parameters. So how we do it, basically, we have a random extraction of some pixels. So we sample some pixels. And of course, as you can see, we're extracting some pixel on all the new bands that we have, because of course we want to preserve, we already have the spatial information, we want to add the spectral information. So we are taking less pixel, let's say from a spatial point of view, but then we want all the spectral information. And then out of this, we're just extracting some statistics. So the mean, the quantiles, the standard deviation, the mean and the minimum and the maximum, and so on. And then we're just projecting this information so that they can be aligned with our feature out of the pre-trained patch embedder. So in this way, we have spatial information and spectral information out of our images. Then these are passed to our untangled attention mechanism. And basically what we're doing, as the name can suggest to you, we're just having different views. Let's say, we are dividing our attention mechanism in different attention themselves. So we have, instead of having just the RGB to RGB attention, that is the self-attention that was already there and is frozen, we're adding three more mechanisms. That one is another self-attention that is just spectral information with spectral information. And then we have two, let's say, cross, let's say, that is RGB to spectral and spectral to RGB. And then we are combining them. So in this way, we are, once again, saving the priors of the RGB. So let's say the spatial information, and we are adding the spectral information. If you put, again, all this together, we can see that, once again, we are replacing not all the attention mechanism, but just, and we're going to see why, with our UAT, and we're replacing our patch embedder with UP. And as I told you before, we already had some clusters that we don't want to destroy, or we don't want to totally to update. We just want to better separate. So again, change the trajectory of them. So to do this, of course, we are fine-tuning our attention mechanism, but we want the norm to be the same. So basically, the attention of the U attention must be the same of the displacement norm of the original attention. In this way, again, we know that we're in some way just using the priors, but refining them. And okay, so this was the methodology. What happened from a results point of view? Is this working? The answer is yes. And of course, as you can imagine, as the models, we use the models that I mentioned to you before. So scale MA, cross scale MA, and dynamic C. Why? Because of what I told you before, different characteristics, different strategies. And concerning the dataset, as I told you before, we wanted to focus on some environmental tasks, let's say, so some tasks in which multispectral information could be really relevant. And so we decided to go for 3 classification dataset and 2 segmentation dataset. For classification dataset, we're using 3 dataset out of GeoBench, while for segmentation, 2 out of PANGAEA. Once again, because these are very well-established benchmarks, so it's kind of easy and nice to use them and to benchmark with other results that are already around. And yeah, of course, for classification, we're just using a linear probe. For segmentation, we're using Ubernet, once again, because it was easier to build on PANGAEA. If you look into the results, once again, a wall of text that I don't want you to get through, but I'm going to help you. We, of course, used the 3 different foundation models, but then we want to also to benchmark different strategy. So we have frozen, fine-tuning, that is like the Oracle, no? It's like the one that we're aiming to arrive. And sometimes we're even better, not always. But then we are using norm tuning, that basically is just fine-tuning the norm of our layers. Bitfit, that is just fine-tuning the biases. Then we have LoRa, Lorenk adaptation, and SLR, that was sort of it was a very cool method that was developed and published in CVPR 2024. That is explicitly shaped for remote sensing. And as you can see, if we look into the results in average, well, DEFLECT is doing well. And this is true for all the models, so the 3 models. And something that is even nicer, as I told you before, sometimes. So for example, in the case of ScaleMA, this is even better than the Oracle. So of the fine tuning, which we're just using 100% of fine-tuned parameters, then to end fine tuning. But something that is even nicer, is that we're using very few parameters if we compare them to the one that are the second best. So basically SLR and LoRa, we're using 1 order of magnitude less, more or less, fine-tuned parameters. Why this? Because DEFLECT can work either just by itself, so as I showed you before, replacing attention with UAT and replacing the patch embedder with the UPE, but also we can combine it with LoRa itself. So basically what we did is to have a LoRa of our UAT. Then we're going to show you also some ablation studies so that I can answer maybe some question like, okay, what if you remove LoRa? But so then if we want to remove, if we want to check some results more in general, let's say more visual results, we can say that, yeah, DEFLECT, also if we consider not model-wise, but dataset-wise, is the best out of this. And this is true also because sometimes models like SLR and LoRa, for some like more difficult dataset like MADOS, are kind of crashing, suffering of gradient issues. If we want also to compare the performance with respect to percentage of fine-tuned parameters, well, we can say, of course, if you have as many GPUs as you want and you don't care about, I don't know, carbon footprint or whatever, just go with fine-tuning, is working better. On the other side, of course, if you have no GPUs at all, but a very small one, you can just go with frozen, you're losing some performance. But if you have some a small computational power, I will give it a try with DEFLECT because they're having very good results with kind of not a lot of parameters to fine-tune. Getting into some ablation studies, well, as I promised, what happens if we're using LoRa or DEFLECT with LoRa or DEFLECT just by itself? Okay, we used as a low rank 16, but even if you're using, let's say, a smaller or a bigger, okay, in this case, sorry, that is not in bold because we wanted to compare with respect to LoRa itself. But also, if you're using no LoRa at all, most of the times, DEFLECT is the best. Is the best to use just DEFLECT with respect to using DEFLECT with respect to DEFLECT and LoRa. But also, DEFLECT is kind of the best with respect to LoRa itself. Just for all the cases, but burn scarce. But yeah, so bar scarce with ScaleMA because number 1 is ScaleMA, number 2 is DynamC, number 3 is cross ScaleMA, number 3 is DynamC, sorry. So yeah, what I just want to show you is that also DEFLECT by itself is working very well. So for example, you can check the 52.9 with respect to other that are 52 in average and so on. So using low rank adaptation is just another reason why to reduce more and more the number of parameters. And then another interesting question that we asked ourselves was, okay, but how about, okay, I said that we're just adapting some of the layers, not all the layers. Why this? Because of course we tried this and we observed that if we're just adapting, for example, one layer, like the first layer, we're not injecting enough information about multispectrum, for example. So we have to inject more information. If we're injecting info in all the layers, so that it means to replace all the attention mechanism with our UAT mechanism, well, we're too much destroying the priors, the spatial priors from the pre-trained RGB models. So we had to find a balance, and the balance was just to adapt the UPerNet layers. Well, as I told you before, for semantic segmentation, we're using a UPerNet, so basically 4 layers out of the, it depends on the size of the model, but let's say, okay, out of the 12 layers are adapted, and well, just 4 of them are adapted, are replaced with the U attention. And of course, this also means that if you're replacing all of them, you're using more parameters. If you're just replacing one of them, you're fine-tuning less parameters. But if you're just replacing 4 of them, is also a good trade-off between how many parameters you are with respect to how many parameters you are fine-tuning. Given this, next steps could be for sure about going stronger in the sense that we want to also try to expand this to hyperspectral images. So if this is working from RGB to multispectral, maybe this could work also from multispectral to hyperspectral. Of course, there are some caveats that we have to care about, but this could be an idea. And also something that we're even more interested into, I would say, because it's something that sometimes is kind of underlooked in our community, mainly because sometimes we're just taking, results off the shelf from computer vision. So we are ignoring some stuff that are not that relevant for computer vision. That is the case of multitemporal images. So in remote sensing, we have a lot of multitemporal images, time series more in general. So we would love to see how this can apply also to time series. And yeah, now then we go to the third part of our talk. That once again was about foundation model, but once again from another point of view. So here we go again. Our task, RGB, change detection, what we want to do now. So we basically use any kind of geospatial foundation model. We try to adapt this foundation model. Now what we want to do, we want to use a diffusion model. So what happens if we use a diffusion model, not for generative purposes, but for discriminative purposes? So for something, someone can say, why? Well, because these have, great success in generation, and we observed. So we know there are a lot of models, Terramine, but we have also diffusion-sat, we have MetaEarth, we have a lot of models that can show very, very promising results. But also we know, both from computer vision, but not only, that these models have really good power in feature extraction. So they can extract very good features. And this is coming both from some exploratory results that we made, like the one that you can see in this picture, but also like giving a look into what happened in computer vision. So in this case, it was very nice to just look into computer vision. And it looks like these are really working also for discriminative tasks in computer vision. And in computer vision, they're suggesting to fuse the feature, because using the feature in a raw way is working, but not that well as if we fuse this feature. So we thought about fusing them. How to fuse them? We found 3 ways of doing this. So basically, we have a generative diffusion model in input. And I can tell you that, this is a diffusion-sat model. And diffusion-sat is using a UNet as a diffusion architecture. And this is a thing that is very relevant, because then in other experiments, we tried also to do this with a transformer-based diffusion model, and it wasn't working that well. So this is also something that we can discuss, but we want to investigate more and more to understand how to make this that I'm going to show you, how to make this work also for transformer-based diffusion model. But basically, given this model and input, so diffusion-sat, we decided to we didn't know which strategy to use, because all of these were kind of novel, let's say, but also interesting from a result point of view. So we shaped 3 different strategies to fuse our feature that are in output of our diffusion model. So as you can imagine, for each block of our unit, we have a feature map, and also from each time step of our diffusion model, we have a feature map. So we have, let's say, a lot of feature maps that, by themselves are H times W times C, so height times width times channels, times blocks times time steps. Of course, the blocks have different shapes because they are coming, as you can see, in the unit itself. There could be smaller in size, larger in channel, and the other way. Basically, after this, we shaped these three fusion strategy. The first one is very, very easy and straightforward. So basically, out of each feature map, so again, just taking one block and one time step, out of each of them, so out of a H times W times C set, we extracted just one learnable scalar weight. And then we're just doing a weighted sum of all the time steps and all the blocks to have our feature in output that can, sorry, maybe I should focus on more on this. That basically what we're doing, after we fuse the feature, then we are passing them through a decoder. And then with this decoder, we want to solve some discriminative tasks that I can show you later, but basically are just segmentation or classification. Segmentation, once again, we use the Ubernet. Classification, we use the linear probing. So basically, back to our first strategy, we're fusing all our feature map in this way. So basically doing a weighted sum with scalar weights and one scalar weight per each block and per each time step. And then with this feature that we have in output, of course, we feed this in the decoder and we are solving our downstream task. As you can understand, this is very simple and very efficient, but there are no fine-grained information, let's say. So we moved on a second one that was this localized weighted fusion. In this one, we have a pixel-wise weight. So basically, out of our H times W times C, we want just to reduce them on the C dimension, so on the channels dimension, on the number of feature map dimension. So we basically move on, for each of these feature map, a smaller feature map that is just a pixel-wise weight scalar, that is H times W. And then we aggregate, once again, all of them, and we feed this into the decoder. As you can understand, in this case, of course, we are having a more fine-grained aggregation in the sense that we can have info on all the pixels. So what we're just compressing, let's say, is just the information about the feature map, but each pixel can come with its own information. And this is very relevant, especially, of course, as you can understand, for semantic segmentation tasks in which we want to have a dense task. And then we add a final model, a final fusion strategy that is a mixture of experts. So basically, we are just inputting all the feature map from all the blocks and all the time step into a router that, of course, is a learning router. And then it's having different subnetworks that are just the experts. And with these experts, then we are having some weights. We are then, once again, aggregating these weights. And with this aggregation, then we feed this final feature map, this fused feature map in our decoder. As you can imagine, this is a way more complex aggregation strategy, fusion strategy, in which we can, on one end, let's say, less explicitly map the interaction. Then, of course, on one end could be better because we can, the machine can understand by itself which are these better interaction, but on the other end, maybe some of them are less explainable, let's say. If we want to move on the results, we use GeoBench. So basically, we use 6 classification tasks and 6 segmentation tasks. And something that is very, very relevant is that, as you can see, okay, most of these tasks are RGB, but not all of them. But while we used diffusion-sat that is using just RGB images. So basically, we fuse the strategies. We fuse the feature maps, extracting these feature maps just out of RGB images. So, for example, in the case of BigEarthNet, of course, we have Sentinel-2, all the 12 Sentinel-2 bands, but we could just use RGB. And this is very interesting because then we still had best results, just again with RGB images, while comparing our model with most of the PANGAEA model, including the PANGAEA model suite. For example, DOFA or Chroma, they can support full Sentinel-2, Sentinel-1 data, but still, they are, for example, with respect to our strategies, so SatDiFuser, that is this suite of these 3 models, is having worse results. Just, I mentioned BigEarthNet, but could be any others like Brickhill and so on. So what we can observe in this is that most of the time, both for segmentation and classification, using the feature in output of this diffusion model is working better than a lot of Geospatial Foundation model. And something that you can ask me is that, okay, but is this true because of what you told us at the beginning? So basically, these features are very, very strong by themselves. So maybe the last 5 minutes in which you talked about fusing feature are totally useless because, okay, if you use raw feature, this is going to work as well. Well, no, because of course we tried this ablation study, and okay, you can see that on method column, when you see TS is time step, and when you see SA is self-attention, when you see R is resonant. What does it mean? It means that, of course, once we're not fusing different time step and we're not fusing different blocks, we're just using one time step and either a self-attention mechanism or a ResNet to project this feature, let's say, into our decoder. And yeah, basically, even if we just concatenate all of them, so even using more parameters, because these results are good, because once again, if you want to compare, I don't know, for classification Eurosat, we can see that we have 94%, that if we compare to this, is kind of the best, not always, but most of the times is the best. So still good results, but with our strategy, this is working even better. So fusing the feature in a fruitful way is leading to better results. And another question that we asked ourselves was, okay, but for time step, imagine that, okay, we cannot fuse the feature because we don't have a computational power, or we just cannot, we don't want to do it. And we are interested in understanding which time step is bringing more information. So basically, in a diffusion model, for generative tasks, of course, we already know that we want to use the most fine-grained image and so on, because we want it to be good looking and so on. But what happens if we want to use out of a diffusion model some outputs that are useful, that are fruitful for discriminative purposes? Which time step should we use? Of course, one can think, okay, just use the time step 0, so the one in which the image is perfectly reconstructed, and this is working the best. Well, something that we observe that is not probably like this is that if there is some noise in it, so generally around 100 time step out of, in our case, what, 700, this is leading to even better results. So basically, if you have some noise in your images, still the feature out of these images are more fruitful for your discriminative model. Then, of course, if you're putting too much noise, this is going to degrade very, very, very fast. But this was very interesting to note. And again, I would be open to discuss with you also about why this happened according to you and so on. So then basically, if you want to move on the next steps also on this, I can tell you that something I already asked you. So, okay, this is working for our diffusion SAT. So SatDiFuser is very shaped on diffusion SAT, but is this working even if we have a model that is dealing with, I don't know, different resolution? So all the Sentinel-2 bands, but what if we don't want to lose some information? We just upsample to 10 meters, or we downsample all to 60 meters. What happens if we want to combine different sensors? Or what happens if we want to add, for example, also SAR images? So how it works? Can we expand this procedure? So basically fusing feature in a fruitful way for discriminative task to any diffusion model. And yeah, more in general, of course, this is very connected to the second question. Is about if the embeddings of the diffusion model are better, let's say. So because in this case, it looked also that when we're using raw feature are better, even just using RGB images. So is this true? I don't know. If you have some answer, please let me know. So then, yeah, going on with our final remarks, I hope that your take-home messages were, let's say, 3. And one is that, of course, benchmark is important because it can really lead to better results. So the new generation of foundation models should be benchmarked in an extensive way so that we can understand why they're working, when they're working, and so on. And on this, I would be very, very open to, again, talk with you about what is missing in PANGAEA at the moment. So, for example, we know new datasets, new sensors, and we are including already Sentinel-3. We want to include some of the spectral data. So, but maybe you know something that, for sure, you know something that I don't know, but I would like to know this as well. Then, of course, connected to this is very connected also to the fact that we want to use more and more multispectral information, but more in general, we want to inject more and more remote sensing peculiarities in these computer vision inspired models that most of the times are really, really strongly inspired from computer vision, but not all the times are really caring about multispectral information, time series, and so on. And finally, yeah, diffusion models and discriminative models sometimes are too much considered two different topics, but they could really go one with each other more often than we can think. And yeah, and then of course I want to thank all the co-authors, because I mean, today I'm just telling you what mainly they did with me and not vice versa. So they were very, I mean, they were the best co-authors I could have. And thanks a lot for this. And yeah, meme times. I hope you have some question. Otherwise, thanks a lot.
All right. Thank you very much for this very interesting talk. Touched a lot of topics. I don't see so much questions yet in the Q&A box. So please, people, if you have something you want to discuss or comment you have, please put it there. There's one question regarding the unit comment you made at the very beginning, where you showed that actually the unit, despite all the advancements, is still a very strong baseline. It's not that easy to beat a well-tuned unit. So the question is whether you can elaborate a little bit more for the choice of a unit model in case we do not have enough information about the data.
So thanks for the question. Of course, this is very related to our set of experiments. And I'm just mentioning this because as I told you, but as I will tell you better, basically our set of experiments was, for example, having some conditions that were kind of general. So in our case, for example, we're having all the labels available for our dataset and so on. So in the case in which you have no strong ideas, let's say, on what is going on in your downstream dataset, in the sense that you don't know about the satellite, you don't know about the modality, we observe that UNet is the one that in average is having better results. And this means that, of course, given that it's lightweight with respect to the foundation models most of the times, and given that it's kind of blind to all these pre-training steps, because we were just considering trained from scratch unit, then this could be a very strong baseline. Also, just to having at least a result that would you expect to surpass. So maybe you can just run a unit and then say, okay, let's check a couple of more models and see, okay, if this are getting better, of course it makes sense to go on. Otherwise, I would stick to the unit. But once again, I want just to say it again that this was also in our case in which, for example, we didn't explore, and we're doing right now, I forget to mention, that we want to do right now 0 shot and very, very few shot. And it's something on which we are expecting that unit is having worse results with respect to Geospatial Foundation Model that are also, this is one of the main advantage of using Geospatial Foundation Model. So this is also something I forget to mention. So thanks for the question once again.
It's actually, I see in a lot of different contexts that the unit is a really strong model, even before the Geospatial Foundation Models, where the transformers were on the rise. I saw a couple of talks where they compared the unit against vision transformers and other transformer architectures, and basically the bottom line was that it's, even for those architectures, it's not that easy to beat a unit, although they're much harder to train. And even if they do, you usually can back distill a vision transformer into a unit, and then you have a much simpler architecture just by knowledge distillation than the vision transformer. So I think this is really something that is quite interesting to see, that the unit is such a strong baseline. What do you think about where is all of this heading? So where do you see Geospatial Foundation Models, let's say, in the next 5 years? Will it be more towards like open and collaborative models, where everybody can contribute, or will they remain dominated by large institutions like ESA or big tech companies that have access to big data, that have access to a lot of compute power?
Unfortunately, we're not part of this big institution GPU wise. But yeah, apart from that, yeah, I would say, I mean, my fear is that it's gonna be still really, let's say, big institution privilege, let's say. So then, of course, as we're already observing, the embeddings and maybe the models themselves. So all the knowledge out of it would be shared with the community. But I see that the development of this will largely remain in this big institution. And of course, this is a big issue from my point of view. But yeah, what we can try is at least to, and this is what we're trying to do also with what I showed you today, to push the community to go open source as much as possible so that all these results can be reproducible, can be adopted, and so on. Yeah.
There was one question in the chat that goes, how do we surmount the unpredictable climate and environmental challenges while carrying out our work and research? It's a general question, I guess.
Yeah, this is more about life. I mean, honestly, I'm very pessimistic about this, so I don't know if you want to know my answer. Yeah,
I mean, there's a direct connection to foundation models, right? Because foundation models, they are really heavy in training, right? So, I mean, it's not like they have the strongest impact on climate change from all the things humans are doing, right? But certainly, it's a different story training, like a couple of foundation models instead of training a couple of units.
Yeah, and yeah, this is also very connected to what we said just before, the question about is this gonna be relegated, let's say, to big institution or not? So my point of view is that, I mean, likely it looks like, and these institutions are at least trying to push some strategies to go with renewable energies, or like reducing the impact also of this. And this is also a topic that step by step is becoming bigger, and we also in PANGAEA start thinking about how to benchmark this impact, so environmental impact. We're discussing it, is kind of early right now, so but this would be something that would be very interesting for us as well. So to understand, okay, this model is the best, but how much more it's impacting with respect to the others. So this is something that can really help to find a good trade-off between doing research but still caring about these things, and try to see, let's say, a third way among the two. Yeah. But again, I'm very pessimistic, so this is the best I can do.
Maybe a different webinar. So maybe as a last question, what do you think? Where do you expect the next major breakthroughs in remote sensing? Is this more from like new models, algorithmic innovations, or is it more from better data, more data, better benchmarks, better evaluation protocols, better training protocols, and stuff like this?
Okay, no, something I forgot to mention that I generally mention is that a problem that is kind of on which I don't know how we can solve this, so it would be very nice to be the next big thing, is that with respect to large language models that are our benchmark, let's say, in what we want to achieve soon, is that in large language models, basically the pre-training task and the downstream task are basically the same. So basically we are masking some tokens, some words, some sentences, and we want just to predict them, making it very, very easy. And in the downstream task, we're doing the same, basically. So we want, I don't know, summarizing, translation, whatever, but we're masking some tokens and we want to predict them. In our case, so in computer vision in general, but in remote sensing even more, this is very, very different, because in the pre-training task, we are masking some tokens, but in the downstream task, then we want them to have out of that token a prediction of, I don't know, the height of the forest. So it's kind of different. So understanding more this would be something that would be kind of cool. So a good breakthrough. And also something I mentioned is that from an algorithmic point of view, and this goes very, very together with having better data, is that some sensors, like for example radar, are really underlooked. So most of these images, like most of the radar, they are just used as images, let's say, into the computer vision model. But if we can create better our data sets, so for example having radar data with info about the angles and, I don't know, the descending, ascending, whatever, and we can include this in the models, then we can have better algorithms. So I would say that maybe it's the easy answer, but to do both would be the best way to do it. And yeah, a way could be this. So understanding better our objective, so our losses, let's say, of our pre-training steps, and this can help also understanding better our data, because we already have the knowledge. We have just to put together this knowledge, because we have remote sensing knowledge and we have computer vision knowledge, we have just to put it together.
Right, and then the last question from the Q&A box. What do you think is more important, the scale or the diversity of the foundation model? So the question goes, how would you evaluate the scale and diversity of a foundation model? Does the scale of data play a more critical role, or does the data diversity matter more?
A great question in the sense that I observed that there are some models that even with very few data can work very well. Like, for example, yeah, dyno-based models are working very well also with very few data. So, and more in general, I would say that, of course, both are helpful, but I would say that to go more with the diversity of data, because in one case, of course, with bigger scale, maybe we can have better performance on some tasks. But if we have diverse data, then we can solve much more tasks. That is something that is more relevant at this moment, because a geospatial foundation model, I mean, to me, it's better to have a geospatial foundation model that can solve 20 tasks, and maybe it's not the best in none of them, but it can be very competitive in all of them with respect to a model that can solve 2 tasks but very well, because otherwise this is just a specialized model. That is something that today is happening kind of a lot, that some models are just autoencoders, just rebranded with a new name that is geospatial foundation model. So I would go more with multimodality, diversity, more than scale, but both are important.
All right. Thank you very much again. There were like 1 or 2 more questions in the Q&A box, but we are running a little bit out of time, so I suggested them to just reach out to you via email. So thanks again for this nice talk. Always nice to hear about the stuff from ESA. And then thank you everybody for being here and being interactive, and I hope you enjoyed it as well. Thank you, and goodbye everybody.
Thank you.